Hello everyone! And before you get on me for recycling content, yes, this is the integral from a couple videos back. But what I wanted to point out in this video is an alternative way to do it, which is arguably simpler, but it is quite a different method. To start off with, I would actually like to show you an incorrect way to do this, in a way, which might seem a bit counterintuitive, but it also does reveal a couple things about this. So, say we want to complex analysis this integral, right? What I started with was using a semicircular contour, as you might expect. So, you draw this, and you'll see here that you wouldn't suspect yet anything's wrong. You'd have your poles, the outer semicircle goes to 0, but there is a bit of an issue, because whenever you do try to evaluate this, you get that the integral, equals 0, because there are no poles inside of there. So it is quite an issue. But then you might take a look at this a little bit closer and realize, wait, hold on. That's arctan. And what I want to do is investigate what exactly is arctan in the complex plane, specifically along this line right here, the imaginary axis. So let's do that real fast. We know that tangent of, say, some theta is going to be equal to sine of theta divided by, cosine of theta. And we can write this, as you know, in terms of the complex exponential. So we can say this is, 1 over I times e to the theta I minus e to the minus theta I divided by e to the theta I plus e to the theta I. Or plus e to the minus theta I, pardon me. And what we're going to say is this is going to be equal to some zi, so some point along that axis right there. And you'll see here that we can actually solve for theta to find arctangent, to define that in the complex plane. So doing that, multiplying both sides by I and manipulating this a bit, we get e to the 2 theta I minus 1 over e to the 2 theta I plus 1, some nice symmetry there, is equal to negative z. And then multiplying both sides by that denominator right there, and combining our terms, we find that e to the 2 theta I, 1 plus z, is equal to 1 minus z. And then what we can do is say e to the 2 theta I is then equal to 1 minus z over 1 plus z. And what we can do now is take a logarithm, and this is essentially where the problems start to get a little evident. So what we have is 2 theta I is equal to the natural log of 1 minus z, 1 plus z. And then because, this is a complex analysis, we're going to add this plus 2 pi I n here, where n is just an integer. And that right there is just because if we multiply by e to the 2 pi I times any integer, that's the same thing as just multiplying by 1. So what we're going to do now is actually just divide by 2i. So now we have theta is equal to 1 over 2i, natural log of 1 minus z over 1 plus z, plus 2 pi, apologies, the 2's and the i's cancel. So we're going to have just pi n here. And then we can also rearrange the natural log here, actually. So, so just to get the I on the numerator, we can just say this is I over 2, and then switch that. So 1 plus z over 1 minus z. Properties of log still apply. So what we've defined now, actually, is just arctangent. So this right here is just going to be our tan inverse of some zi. And what you'll note here is that everything is good and fine with this function up until z exceeds 1, or negative 1 for that matter, but we're only going to worry about the positive part of the complex plane, or imaginary bit. So as soon as z gets to 1, you'll see that we have an asymptote right here. And then as soon as you go even further, what you get is the natural log of some complex number, which we know is going to result in, yes, a complex number, but there are always, again, multiple things that can lead to that. So it's because of this that this method and this contour does not necessarily work. And instead what we need to do is define arctan two ways, one for the right side and one for the left side. So what I mean when I say that is we're going to be doing a branch cut. So our contour is going to be looking like this now, where that little circle, or the extra one, is around I. So right there is I. And we're integrating along the real axis still, but we're also going around the parts of the imaginary axis to where this doesn't have a very clear value. So, doing that, we can actually evaluate this integral using the residue theorem. So, let's do that, shall we? I'll actually do it over here. So we have our contour on screen. So we have our integral, our whole line integral. It's going to be equal to 0. That's just because of the residue theorem. There are no poles in here. Now, if you suspect maybe that there is something at 0, it actually is just a removable discontinuity, not a super big deal. But we also know that we can split up our line integral. So we can say, our total line integral is also equal to the integral over, say, I'll call this gamma 1, and then the right side gamma 2, and the right side gamma 3. So the integral over gamma 1 plus the integral over gamma 2 plus the integral over gamma 3. And we know that, the integral over gamma 1, this right here, is just going to be I. This is what we want to solve for. But it's these we actually want to evaluate. So putting this in terms of those, we have that I is equal to negative integral over gamma 2 minus the integral over gamma 3. So now all this is a challenge of evaluating this arctan along that imaginary part of the axis, or that part of the imaginary axis. Word order matters. So let's do that real fast. So, let's start with the integral over gamma 2. This right here is going to be equal to the integral from infinity I to I. And again, that's just because we're going, from like infinity, but infinity is going to be along the imaginary axis, so we add an I there. And then all the way to I, because we're integrating downwards. So that right there, and then we're going to have our arctan squared of some z divided by z squared dz. And now to simplify this a little bit, what we're going to say is u is equal to, negative I t, and then du is equal to negative I dt. That way we can just get our bounds to a place where they actually are, just a little bit nicer, and that we can actually evaluate them. So what we have then is the integral from infinity to 1 of arctan squared. What we have is a negative I t. Oh, I do apologize. I'm so used to doing u subs. Goodness me. That should be a z. Yes, okay. Those are z's. I'm sorry. been doing too many u subs. But the point still remains. We have arctan squared of minus I t, but the minus sign we can throw out of the arctan because it is an odd function. So what we have then inside it is just an I t or a ti. Order doesn't matter. We have our dt. I'm going to throw a negative I out front. And then in the denominator, what we have is z squared, but negative I squared is just going to be negative 1. So we have minus t squared right here. And you'll see that our minus signs are going to cancel, but I'm just going to use one of them to just kind of flip the bounds real fast. So we have 1 to infinity. Okay. And now the integral over gamma 3, we're going to do it in the same way. The only difference being that the bounds are flipped, so it's just going to be negative all of that. So essentially the same thing, but just positive I. So you have I times arctan squared ti dt over t squared. And now you're probably thinking, well, wouldn't those just cancel and equal 0? No, actually. And the reason for that is because arctan, as I've said before, is going to be defined differently depending on which side of the branch cut you're on. And that's the way we're going to evaluate this integral. So let's see what arctan actually is. So, moving over here. What we can say is that on the right side, or I should really say along gamma 2. So along gamma 2, what we can say is that we have this n right here. We have n is equal to 0. And then on the right side, over gamma 3, we can say that n is equal to 1. Because after all, we're just adding, 2 pi I, essentially. And it's going to be sort of equivalent, at least. So what we have for gamma 2 is then I over 2 natural log of 1 plus z over 1 minus z. But here's the interesting thing right here. In order to actually integrate this, what would be awfully nice is if we could express this as not as just a logarithm of, some number, because after all, this right here is still going to be complex for z is greater than 1, and that's where we're integrating. So what would be nice if we could actually express this natural log is not as just normal natural log, but as the absolute value of this. And we can just add I times argument of 1 plus z over 1 minus z. So here is just an alternative definition of the complex logarithm, and again, that's just so we can integrate that easier. Now, this part right here just becomes a question of what is the argument of 1 plus z over 1 minus z? And the answer to that is perhaps a little simpler than what you might think. So imagine this is our complex plane, and we're only considering values, z is greater than 1 because, well, that's along the path we're integrating. So if we say z is, 2, well, we have 1 plus 2, and then over 1 minus 2, which is negative 1, in the denominator at least. So we're going to have, negative 3, and it doesn't really matter. But the point is, as we increase z, it's just going to get more and more negative. So even though not the direction, but even though the magnitude of our value is changing, the direction in which it's going isn't. It's always going to have the same angle of just pi. It's always going to be along the negative part of the real axis. So our argument is actually just pi. So right here we have just an I pi. And we can actually simplify this even further by distributing this I over 2. So I'm just going to erase that parenthesis. And distributing this I over 2, we actually have 8 minus pi over 2. So next what we have is this integral over gamma 3, where we're going to say n is equal to 1. So it's going to be the same thing. So we have I over 2 natural log. I'm just going to throw in the absolute value right away this time. And then plus, we can say plus pi, because we're going to say 1 plus pi I, and then we're going to have our extra plus pi at the end. And distributing, we find that it's actually the same, just that we have a plus pi over 2 instead. So now that we have these, all we have to do is square them and do a bit of integration, and we will have our answer. So I'm just going to write down what these are. Actually, no, I'll put them right here. So then the integral over gamma 2 is equal to the integral from 1 to infinity of I over 2 times the natural log of the absolute value of 1 plus z, or t I should say, t over 1 minus t, and then minus pi over 2. And that is all going to be squared, divided by t squared, and then don't forget we have our minus I out front, dt. And then for gamma 3, we have a very similar thing. We're going to have the integral from 1 to infinity, don't forget the I, of I over 2 natural log of absolute value of 1 plus t over 1 minus t minus plus pi over 2 all squared over t squared. And you'll remember that our actual integral is just going to be the negative sum of these two. So let's just go ahead and add these together real fast. So integral over gamma 2 plus the integral over gamma 3, and we'll just throw a negative in front of whatever we get to actually find our integral. This right here is just going to be, well, the integral from 1 to infinity because the bounds are the same. What we can actually do is just factor out an I, so we can just put an I out front. And what I'm going to do is also factor out a 1 over t squared so that we can just focus on the terms that are going to cancel. I'll even put it in a different color. And now we just have to expand these out. So this first term squared is going to be, we're adding them together, but because of the different signs, it's as if we're taking like this bit and like subtracting it from this bit, like minus the negative. So we have I squared over 2, which is just negative 1 over 4, natural log squared of the absolute value of 1 plus t over 1 minus t. And then doing the other term, we're going to have a plus pi squared over 4. And then we're going to have a plus, 2 pi I over 4, but we can simplify that to just pi I over 2, a natural log of the absolute value of 1 plus t over 1 minus t. And then we're going to have the same thing, but with a minus sign for the pi over 2. So squaring that, we find, obviously I have minus sign and then all this. This first term is not going to change, if I can write it right. Natural log squared of 1 plus t over 1 minus t. And then we're going to have still a plus pi squared over 4, and that is just because negatives cancel. But instead we're going to have a minus, not 2 pi I, a pi I over 2 times the natural log of 1 plus z over 1 minus z, close parentheses, and then, actually I should make the parentheses match color, shouldn't I? dt. Oh, that looks kind of nice, actually, my gosh. I should start color coding more often. Okay, but color coding is not the point of this. The point of this is that we can see what cancels. So you'll see that we have a nice little minus sign there, meaning that that cancels with that, and that cancels with that. And which leaves us with these two right here being addition signs. So what we can write is that this integral is just equal to I times the integral from 1 to infinity of 1 over t squared, and then times, pi I times the natural log of the absolute value of 1 plus t, over 1 minus t dt. And this integral actually is not super terrible to evaluate, and the reason for that is because we can just say u is equal to 1 over t, and we have du is equal to minus 1 over t squared dt. So, throwing all the constants outside of the integral, just to simplify things quite a bit, we have a minus pi times the integral, from 1 to 0. The t squareds are going to cancel, and we're going to get an extra minus sign, which is this right here, but I'm just going to use that to flip the bounds real fast. So from 0 to 1 of the natural log of, 1 plus 1 over t over 1 minus 1 over t, but we can just multiply the top and bottom by t, so we really get the same thing. We get t plus 1 over t minus 1 dt. And now we can just straight up evaluate this integral using, really just BCE techniques, like Calc 2 stuff. So we can say, I'm just going to omit the minus pi for now. We have natural log of t. Oh my goodness, I can't write a t. t plus 1 minus natural log of t minus 1. The absolute values, of course. Integral from 0 to 1 dt. And to evaluate these, we could do integration by parts, but just for the sake of brevity, we're just going to say that the integral, well, not from 0 to 1, pardon me, the integral of just say natural log of x dx is going to be equal to x times the natural log of x minus 1. I suppose these should really be like absolute values right here. But that's what we're going to say. We're just going to use that real fast. So what we have then is something quite long, but it's not too terrible because most of the terms go to like either 0, 1, or 2. So it's not awful. So we have t plus 1 times the natural log. The absolute value part right here doesn't actually matter for this first bit, but does for the second one. Yes, I did close on my parentheses. So we have that for the first one. And then we have minus t minus 1 times the natural log of the absolute value of t minus 1, pardon me, minus 1. Oh, the parentheses are closed. And that's all evaluated from 0 to 1. So evaluating that, plugging a 1 to everywhere, we find that that whole second bit actually goes to 0. And that the first bit we have 2 times the natural log of 2 minus 2. And then plugging in 0, so minus, where we're going to plug in for 0, we have, we plug in 0, we find that we have 1, okay, times the natural log of 1, which is 0, and then times negative 1. And then we're going to have minus, we're going to plug in 0 here, minus, we're going to have another negative, there's way too many negatives here, man, times the natural log of absolute value of negative 1, which is just natural log of 1, which is 0, minus 1. So let's just go through here real fast and just say that's positive, okay? In distributing this sign, we have that is all positive. So this is a very, perhaps convoluted way of saying that this right here is just, these terms cancel. It's negative 2 plus 2, 2 natural log 2. And then you'll remember that on the outside we had a minus pi. So our total integral, or I, is equal to negative pi times 2 natural log 2, or, in a kind of nice form, we have 2 pi natural log of 2. And that right there is our answer. So I hope you all enjoyed this video in a slightly different take on this integral. And I'll see you all in the next one. Thank you for watching.